All right, so hello and welcome to all the students. So here we are with another interesting session for you. So here I am, Arjun from STEM&Space, and today again I am with Dr. Mila Mitra. Say hi to ma'am. Yeah. So yeah. All right. So thank you, ma'am. So basically, students, in today's session, we are going to learn about a very special telescope. You see, in astronomy, when we want to understand about the universe, right, the one of the major tools and one of the very few tools that we have to explore the universe is a telescope, right? Because we cannot virtually reach we cannot go and touch everything, right, in space. We are not that advanced till now. So to explore most of the things in the universe, we still use a device which helps us to have a peek at them, to look at them, and we get a more understanding. And that is a telescope, right? So in this regard, today we are going to talk about the most advanced telescope till this date, right? That is the James Webb Space Telescope. We are going to talk about the James Webb, like everything about it, and a few more interesting facts about it, and when it is going to launch. So that is going to be a very exciting period for people in astronomy field. But let's see if you guys can share some of that excitement. So yeah, Milan, you want to say something?
So hello, everyone. And we've been seeing you with different sessions for the last few days. So today we are indeed very excited because this is going to be the big news for the end of the year. That's when the launch is. So we are preparing you and getting you all excited so that when the launch happens, you know that you're witnessing a launch of a mission that will be really famous for the next decade. So yeah, let's.
So yeah, let's begin now. All right, so students, so basically I'm going to share a few facts with the help of a presentation with you. Yeah. So let me just share my screen and let's hope that everybody can see this. Yeah. All right. So with this, let's talk about the James Webb Space Telescope, what exactly it is. So I hope that have you all heard about a telescope named Hubble Space Telescope? Most of you should have, right? And you would have. So the Hubble Space Telescope is actually the most advanced telescope that we have in space because it has given us so much of knowledge, so much of data that it is virtually the backbone of most of the things that we know in astronomy for the last 30 years. But here is the thing, that Hubble Space Telescope, no matter how marvelous it was, it is in space for the last 30 years now. Right. So it was launched in the year 1990. Just imagine it is 31st years, right? So it is that old. So that was the time when we did not even have the smartphones, right? So just imagine how old the technology is. So obviously, right, the Hubble successor needs to be there. But the thing is that building a successor of Hubble was not that easy. It was a very difficult task. So we are going to discuss about that, and that successor of Hubble that we are talking about is this, the James Webb Space Telescope. This is how that telescope will look. So let's just start learning about this telescope a bit more in detail. Yeah. So, all right. So first, talking about the name, the James Webb Space Telescope. What does this name come from? So this name of James Webb Space Telescopes come from a person named James Webb. Now, this James Webb was actually one of the administrators of NASA, right? He was the person who was responsible for launching one of the, what we say, basically handling the NASA, making sure that everything runs smoothly during one of its most turbulent and one of the most important period in NASA's history. That is the launch of Apollo 11, the entire Apollo program. He oversaw that. And that is the reason, to honor him, NASA decided to name the next generation of space telescope after this. And the second thing, obviously, it is a space telescope. Now, what is a space telescope? It is actually a telescope which is there in space, right? So if I talk about the James Webb Space Telescope, or in short, the JWST, it is a successor of Hubble. Now, it is the largest space telescope ever built. And why it is the largest? Because to make this telescope better than Hubble, we needed to make it bigger than Hubble, right? Because the mirror is what we say is the most important part of a telescope, which helps it to gather light. So the bigger the mirror is, the more light it can gather. It is as simple as that. And we wanted to gather as much light as possible. So basically it has the biggest primary mirror in any space telescope that we have made till now. And basically it will be peering into the space in the infrared regions, and we will expect to look at the oldest of the stars and the galaxies that have formed at the inception or at the beginning of the formation of a universe. So that is what we're trying to achieve with it. Let's just learn a bit more about it. So the first point is, if we are to basically send a telescope, why to send a telescope in space? Like, why can't you do it on Earth? Right? And you can basically create a much bigger telescope on Earth than you can ever send it to space. Then what is the need of sending a telescope to space? Isn't it? So let's see what is actually the reason for it. The reason we need a telescope in space is this. Our Earth has an atmosphere. Right? You guys must be thinking that I'm saying this as if it is a bad thing. Not really for our survival, but for the observation, for the astronomy observation, in some regards, yes, it is actually a bit of a bad news that we have atmosphere. Why is that? The reason is that actually, if we are to say like our atmosphere, what does it do? Our atmosphere, it actually protects us from most of the harmful radiations coming out from the coming to Earth from the outside space, right? It includes the harmful UV radiations coming from the sun and other harmful radiations coming from the other parts of the universe too. Right? That's what the let's say atmosphere does. But what if I were to tell you, like all these radiations, that the term that you listen, these radiation is actually a form of light. We call it the electromagnetic radiation. So every term that you have heard, like the radios, the microwaves, like say the UV, the X-ray, and even the gamma rays, they all are type of light only, right? So actually the visible light, the light that we see, is also a part of that electromagnetic spectrum. Now the thing that the atmosphere does is it only lets a fraction of this entire electromagnetic radiation or the entire radiation of light. It only allows a very small fraction of it to penetrate into the Earth's atmosphere. And that is the reason that if we are on the atmosphere, we can only study that part. We cannot study if it does not reach Earth, right? So to do that, what we need to do is we need to take a telescope to a place which is outside the atmosphere, and hence the space telescope. Right? So that is actually the need for a space telescope. You need something to move out of the atmosphere so that you can capture all the lights that is available to you. Right? So that was the need of it. And because of this need, we have been sending the space telescopes. We have been sending telescopes in space for more than 40 years now. Yeah. So again, if I were to tell you the advantages of space telescope to a ground-based telescope, the first advantage, obviously, as you must have guessed, is the atmosphere only. Because if you think about the atmosphere, it is a layer of the gas which extends till thousands of kilometers from the Earth's surface till its highest point, right? That is how thick our atmosphere is. Now, if it is this thick, it means that in this layer, there are some regions which are very hot. There are some regions which are very cold. There are some regions in which the wind blows very fast. So basically, any light ray which try to enter into the atmosphere, it cannot go unaffected by what the atmospheric conditions are, right? And because of that, the data or the light that you're getting on Earth, it is not a purest form of light. It is somewhat manipulated by our atmosphere. This thing get even more exaggerated, and you can see it very prominently when there is some sort of windy conditions when you're observing on Earth. Let's say here, if you can see this picture shows two places, right? One place, it is towards the windward side of the ocean. So the winds blowing from the oceans are basically very laminar flow, and it is a very easy flow. So if the conditions are like that, the light rays can come without any hindrance, and you can basically capture them and you can do your observation. So if you are to observe the planet Jupiter from site A in this case, this is a kind of image you may, let's say you are expecting this kind of image, or you are getting this kind of image from site A. Now, is on site B, if the flow becomes turbulent, if the air will become very turbulent and all these things happen, so what will happen in this case? In this case, when the light try to enter, it won't be traveling straight. It actually will be getting relayed, or maybe getting fluctuated by all the windy conditions. And this is the reason that even if you keep all your equipment safe, you cannot get the perfect observation. So this is one limitation of putting your telescope on Earth, because you have to look for the days where you can do your observation, because not every day you will be able to do the observation. There are cloudy conditions, there are rainy conditions, and many other conditions which prevents you to do that. Second thing, on Earth there is light pollution. We all know that there is light, unwanted light keep on coming to Earth from different sources, right? We can see many things in our cities also. Like in cities, we cannot even hardly see 1 or 2 stars, right? So if you have to put a telescope, we need to go to an extremely dark location, which is getting harder on Earth. And the second thing is, like you will learn later in this session, that to make this telescope work, you actually have to work in very cold temperature. You actually have to keep this equipment at a very cold temperature. And to achieve that, the best place is space, because as you all know, space is very cold, right? So this is the reason why space telescopes are better, or the advantageous than the ground-based telescopes. And that is the reason we go with so much hassle of sending a telescope to space. Yeah. Now let's talk about one of the rays over here, the infrared rays. So remember, if I just a few slides back, when I was showing you the entire electromagnetic spectrum, there is a term you heard or you must have seen, which is called infrared. Now this infrared, it is actually very, very interesting, or a very special kind of rays, right? So why is that? Let's learn that. So let me first tell you about all the rays which are present in the universe. And what their advantageous points are. So first thing, if I were to talk about the gamma rays, now these gamma rays are actually the highest, the most dangerous radiations that you can get, right? And these rays actually emerge from nuclear reactions on Earth, or in space, they actually come from the very high, the places which have the highest, energy. That is neutron stars and black holes and all these sort of things. So if we are to study these gamma rays, we can actually figure out all these regions in space, right? Then comes the X-ray. Now this gamma ray, okay, coming back to gamma ray, this gamma ray, you see, they are very high energy rays. And because they are very high energy rays, they can penetrate into anything. And when they penetrate into anything, that is the reason that you have to, if you will see in the movies and all, that if a person gets into a zone which has gamma rays in it, he has to wear a hazmat suit, right? What exactly it does, it keeps those rays away, right? So these are so powerful. Then a little less energy than that is X-ray. Now X-ray also is very penetrative. It is also very high energy. And this is the reason that when you take your X-ray can actually reveal your bone. You cannot see your bone like this, but because this light is so high energy, it can literally get into your skin, into your bone. And when it does that, it can click a picture of those bones, right? So that is X-ray. Ultraviolet rays, little less energy, but very highly penetrative, right? And then comes the visible light. Now this visible light, it is actually a very small region of that entire light spectrum, which we call the electromagnetic spectrum. And when it is a very small fraction, it means that we can this region is the region which we can actually see. So this visible region, you must have heard that the colors of the rainbow, the 7 colors, those colors only make this entire visible region. That is red. Okay, you know, right? It is called VIBGYOR: violet, indigo, blue, green, orange, yellow, red, right? This is the VIBGYOR. So all these 7 colors make up the electromagnetic spectrum. Now the blue region is the higher energy region. The red region is the lower energy region. So the thing is that basically when you see something is very high energy, it will emit blue light. If it is very low energy, it will emit red light. But it is not exactly true in every case. Yeah. Now here is the thing. Lesser than visible is the infrared, and then comes the radio waves. So radio waves are the ones which you use to see here radio and all of that, right? But the infrared is something very interesting. You see, these infrared waves, they are actually bigger than your visible light. So if they're bigger than your visible light, they can actually go around stuff and see what is at their back, which others cannot do. What X-ray will do is X-ray will penetrate your bone, basically penetrate your skin to your bone and give you the picture of your bone. It cannot move around your body, but the infrared can. Infrared can move around small stuff so that to see what is actually at their back, because they are so big, right? So this is what the infrared is. And when these infrared are so, let's say, and this is the reason that this infrared possesses a very interesting quality, that they can actually penetrate a bit behind your, what we say, the very small particles which are in front and show you at the back, but it also shows you the heat of it. You must have seen some pictures like this, right? This is the infrared picture. This shows the heat radiations coming from a person. So if you see that this table over here, this chart, it actually shows the temperature of it. And in this temperature, you can see that 93.4 should be his ideal temperature in Fahrenheit. And the darker it is getting, it is actually the colder and colder regions. So it is showing that. But more than that, take a look at the t-shirt of this person. This infrared rays are what they are doing is they are actually moving beyond his t-shirt and revealing the, what we say, the heat signatures coming from his shoulder and his arms, right? So that is what the infrared is. Now this quality of infrared is actually very beneficial to us when we are to learn the space. Why? Because in space we have vast majority of clouds which can span light years in distance. Those clouds are called nebulas, right? So these nebulas and all these different basically gaseous structures in the universe hinder us from or prevent us from seeing what is at their back. But infrared can do exactly that, right? It can pass through those clouds of nebula and reveal the stars, the heat coming from the stars which are behind this nebula, right? As you can see in the pictures on the picture on the right. The picture on the left, it shows a very beautiful nebula, but you cannot see any stars at the back of this nebula. But the picture on the right, it is passing through that nebula, so you cannot see any major gas in it, but you can see 1,000 more stars in the same frame, right? So this is what this infrared is, and this is the reason that we look at the space in the infrared wavelengths. The thing is that our universe is actually very big and very vast. And more than that, the universe is expanding a lot. And when the universe is expanding, what exactly it is doing is it is moving farther and farther away. So to look at the earliest of the universe, we have to peer very far away in space, right? And to do that, the best tool we have is the infrared imaging. The reason being, this infrared can actually surpass some very small hindrances which is in the front and let you see the interesting star patterns or any other stars or the oldest known stars and galaxies in the universe surpassing those hindrances, right? So when we see that, then there is another concept comes. All right, so that concept is actually of the redshift. You see, in light, light is actually very special. It shows some of the very interesting features or some of the interesting properties that we have observed. Now, this particular redshifting, this was discovered by a person named Dr. Edwin Hubble in 1900s, in 1930s. So when he did that, it was a very big discovery of its time. And because of that, the first telescope we sent, the last major telescope we sent, the Hubble Space Telescope, was named after this person, right? So what exactly is that did he find? He found out that basically when the particles, when the light particles are reaching you, they should reach in white color, because obviously like the visible light is, the color of the visible light is white, right? It is deflected into the component of 7 colors of the rainbow, but when we see that light, we see the white light. Like the light coming from the sun, it is white light, right? But what he found was, when this particle was coming from a star or an object which is coming towards you, then this particle tends to shift a bit towards the blue. So the light that you see is actually a bit of a blue light. And if an object is moving away from you, then the light coming from that object is shifted a bit towards the red region, right? So when he found out that, all he had to do was, he had to figure out basically, if the particle, if the light he is receiving, is it blue or is it red? If it is blue, it means it is coming towards us. If it is red, it is moving away from us. And this is because of the same reason that we know that Andromeda galaxy is going to collide with the Milky Way. Because the Andromeda galaxy, the light coming from Andromeda galaxy, it shifts a bit towards the blue. And so since it shifts a bit towards the blue, we know that actually it is something which is coming towards us, and then we were able to calculate that how fast it is coming and when it is going to collide to our Milky Way, right? But the thing is that as the universe is expanding, most of the stars are going away from us, and as they are going away from us, they show the redshift. So to observe these red shifting stars also, we need the infrared telescope. These are some reasons that why we actually need the infrared telescope. Now, when we talk about the Hubble actually observed the universe in something called near infrared. Near infrared is basically something which is just beyond the visible light. And that is the reason that it was able to show us so much about this universe and some of the most amazing discoveries it was able to make, right? But the James Webb is a bit different from it, right? Now, what exactly is the James Webb, and how is exactly it is the successor of this Hubble? To explain that, now I will hand this session over to Dr. Mila. So Mila ma'am here will be talking about what we say. Yeah. So she'll be talking about yeah, the James Webb Space Telescope, and basically all the discoveries it was able to make, and some of the important features of it, that why it was made the way it is, and some of the important equipments on it. So to take it forward, I would like to hand it over to Dr. Mila. Mila, you can take this forward and please tell the students a bit more.
So, yeah, hello everyone. So you just heard from Arjun about some of the science that has gone into why the JWST was designed the way it is. So now I'm going to tell you all about the JWST. Okay, so JWST is the James Webb Space Telescope. It's a partnership between 3 different space agencies: NASA, European Space Agency, and Canadian space agencies. And they are all involved in the building as well as the instruments. So it's a worthy successor to Hubble Space Telescope. So it's not replacing Hubble, because Hubble is still running. But, you know, for a decade, those of us in astronomy have seen so many discoveries coming out of Hubble Space Telescope, and it has improved our knowledge of our universe so much. And now JWST is going to extend what Hubble has provided. So it will try to look further, it will try to look deeper. So everything is stronger. So let's see how it is going to improve on it. Okay, so what are the objectives of the JWST? There are 4 main.
Yeah, I think it is working now. Just give me a second.
Okay, so meanwhile, I'll just talk you through while Arjun sir is trying to refresh the streaming. Okay, so I'll go back a little bit. They were stuck at the first. Yeah.
So,
Okay, yes. The stream has stopped, I think. Do you just want to stop and restart the stream?
no, it won't work that way.
Is it working now? Maybe?
Yes, ma'am, it is working now. You can continue. Thanks.
Yes. Do check on the YouTube also. Okay, so yeah. I sorry kids, I think it froze for some time. The streaming had stopped. So now we are back online. Uh, yes, the objectives of the mission, I've already talked about that. Okay, so now I'll come back to this slide, which is the universe is expanding. So the first stars and galaxies that form are the furthest away right now. They've made it out very far, and the light from them has now shifted from visible to mid-infrared. So if Webb telescope wants to look at objects that are so far away, it has to really shoot for the mid-infrared, and that is a capability that it is going to try much more than Hubble. Okay, so JWST, if it can actually, it's going to try and see the first stars and galaxies that formed more than 13 billion light years away from us. So JWST, that's why we'll look at objects in the infrared. We'll look at the universe in infrared. So how will it look back in time? Okay, so I'm showing you an image, and I'm sorry, for younger kids, this might be a little more than they understand, but for the older students, you see at the bottom of the picture, the Big Bang. So that's the first known thing that we know of how the universe formed from one dot. One dot was called a singularity, and it just exploded. That's the Big Bang. That was about 13.6 billion years ago. But even after that, there was a gap. We could not see anything. I mean, there was nothing there to see for some time. That's called the dark ages. The first galaxies and first stars were a few 100 million years after that. And that is the stage which Webb is going to try to see. The first visible, or it's called the first luminous objects, which is the first galaxies and stars. Okay, so in this image, you can see on the right-hand side, the Big Bang. A few hundred years, so this is what actually the Big Bang has already been studied by a couple of missions, such as the Cosmic Background Explorer, WMAP. They were all able to look at the universe in microwave radiation, and they were able to see signs of the Big Bang. But they could not look, they were only targeted for that. No satellite so far has looked at the dark age, and few hundred millions years after that were the first stars and first galaxies, and that is what JWST is aiming for. And Hubble, if you see below the top arrow, Hubble, the Chandra, they have all looked at deep field. They were able to see the first stars, but they were able to see them as toddlers, whereas JWST will see them as babies. So JWST will look out much far into time. And why is that important to know? Because we are born from stars. Our solar system, our galaxy is formed from those stars. So we want to know how the first stars formed, how the elements in the universe came to be, and so on. We'll get answers to those kind of questions. Okay, so that's, again, so the main point is Webb is trying to see very far into time, which means more than 13 billion years ago. So for that, it needs to look at mid-infrared, and no other telescope have done that so far. So that, why haven't they done it? Because that creates its own challenges to try to observe that far in time. We'll talk about some of those challenges. The second objective is galaxy formation. So those who follow space photographs, images, they might have seen that there are so many images of Hubble galaxies that Hubble has provided. So it's been found that earlier galaxies were clumpy and small, and now the galaxies that are much newer are very evolved ellipticals and spirals. So again, if you look at the first galaxies that Webb is trying to do, they might be able to provide answers on how the galaxies evolved from such small clumpy objects to such evolved objects as we see them now. JWST will also look at star formation. Arjun sir showed you this image. It's called the Pillars of Creation. It's a very famous photograph by Hubble. And stars are formed within gas and dust. But unfortunately, gas and dust hide the stars. So telescopes that observe in the visible are not able to see through them. But they emit heat. So they are visible in the infrared. And if you see this picture, you can see so much more in it. And both of these are pictures by Hubble. The left-hand side is visible and the right-hand side is near infrared. So if you can see so much more in the near infrared, then imagine what you can see in mid-infrared, which is what Webb is going to try for. Okay, so what is the difference going to be between JWST and Hubble? The overall size is not that much different, but the mirror size is the most important thing. Now, JWST needs a really big size mirror to attempt to look back that far into time. It has to collect a lot more light. So the Hubble mirror was 2.5 meters in diameter, and you can see a person placed next to it. It is about that height, a little bigger. JWST has a 6.5 meter diameter mirror. So it's 3 times the diameter. Wavelength, JWST will look more at the mid-infrared, whereas Hubble was more in the visible and near infrared. Hubble, if you can, I'm going to explain this image later, but Hubble was placed very close to Earth in Earth orbit at only 570 kilometers, whereas Webb is going to be placed very, very far away at what is called the L2 point, which is 1.5 million kilometers away. Okay, so coming back to how big is JWST? If you look at Hubble, it's about the size of a big tractor trailer. Webb is the size of a big Boeing airplane. Okay, so now again, comparing the sizes of different telescopes, Webb is one of the biggest telescopes that has ever gone. Hubble was a little smaller. Spitzer was much smaller. Okay, so again, comparing the mirrors, 2.4 meters, 6.5 meters. So now we have some problems. Otherwise, many other telescopes would have tried to look this far back. So what are the challenges that have come up from these objectives? So to look that far back in time, you need to have a giant primary mirror because mirrors gather light. So the bigger it is, the more light it will gather. It's just like a rain bucket that gathers water. How will such a large mirror be constructed? How will it be launched? Where will you get a launch rocket that will be able to carry such a big mirror and place it into space? So you're going to need a super launch vehicle. Also, like we've said many times, JWST is going to measure infrared, and you are going to get very, very faint signals from the furthest stars. But as we've said, objects themselves can contribute heat, like the instruments, like the telescope. If they get heated and they contribute heat, then it's going to mess up the faint signals that you're looking for. So everything in the Webb telescope has to be super cooled. It's called cryogenic cooling. So you're going to have to worry about the mirror, and you're going to have to worry about how to keep the instrument, the mirror, and the telescope super cooled. So with these challenges, how did JWST deal with that? They've come up with a lot of innovations. These are called marvels of technology. So let's talk about them one by one. Hubble has marvels of engineering that are amazing. They'll be used in future telescopes. In fact, some of these results have even started contributing to Earth-based uses, such as the mirror technology has, contributed to how doctors can measure eye and ocular problems. Okay, so let's talk about the giant mirror. How will that be built? Now, the JWST, as you can see, is 3 times larger. And we need that 3 times larger because to look that far back in time. But this size mirror has never been launched into space. If you take a mirror like Hubble and just make it 3 times larger, it's going to be too heavy for launch. And this huge mirror will not fit in any rocket. So how was this solved? So we use this. So Webb came up with material that is strong but very light, and this material is called beryllium. So beryllium is very light, strong, and it holds its shape. So this is the material used. Also the size. So it was decided to make this giant mirror in sections that would be pasted together over a backspace. Okay, so if you make mirrors like this in circles, you'll see that there's a lot of space left in between. So that design was ruled out. If you place squares next to each other, there's no space in between. But what you want is an overall structure that is circular, because that creates the best focus. Okay, so this was also ruled out. So the way to go was putting hexagonal mirrors sections together. So there are 18 hexagonal mirror sections that are placed together, and they make an overall structure that is a circle. Okay, so hexagonal segments join to make a roughly circular shape overall. And there's a high filling factor, means there's no gap. Okay, so that's what it looks like. Additionally, because they're sections, they lend themselves to folding. So another thing that will happen now is, so additionally, why we post these pictures in yellow? Because they are coated with gold, because gold makes it more reflective to infrared radiation. Okay, so the sections make it easy to fold. So now this is going to be a folding mirror. Okay, so how is it going to work? It's like a table. You can fold the edges. So like that, you can fold the last 3 mirrors on each side so that they fold and it becomes like a much smaller sized mirror. So this is a very new technology. It's never been used. Folding mirrors, it's like origami. And it's going to unfold after launch. So now here's another marvel of engineering. I said that this telescope needs to be super cooled. How is that going to happen? 2 or 3 things will go towards that. One is the giant sun shield. Look at the pink structure here. That's the sun shield. So this is a 5-layer sun shield, which is huge. It's the size of a tennis court. So each of the layers is made of lightweight material called Kaplan. So they're very light. Each layer is as thin as human hair. Here it looks wider, but that's what it is. And the layers have vacuum between them, so they reduce the temperature as you go from the hottest side to the coolest side. The coolest side is where the mirror and the instruments are kept. So you know how we use sun shields that are SPF 30 or SPF 50. So this is going to be approximately SPF 1 million. Okay. Now the sun shield is also foldable for launch. So both the sun shield and the mirror are going to fold in like origami and fit into the rocket. So let's take a let's take a look. How will they fit inside? Okay, so that's the JWST. The mirrors fold, the sun shield folds, and it all can fit into this very powerful launching rocket called the Ariane rocket, Ariane 5 rocket. Okay, so that's an amazing design. We haven't had any technology before where the spacecraft, where the mission, where the mirror folds up like that. So it's going to be stored like this for, all folded up, and then it's going to unfold after launch. Okay, so here's another thing that is in the design to keep it cool forever, which is it's going to be placed at a very interesting position called L2. Okay, so L2, L1, there are 5 positions called Lagrangian positions. Okay, so these are the Lagrangian positions, and these are positions where if you place a telescope or a mission, it will stay stable. It has equal, the gravitational forces by the sun and by the earth and the object, they balance out each other, so they can stay fixed and mostly in that position. So many solar telescopes are placed at L1, and Aditya, our own, will also be placed at the L1 position. Now, L2 is very far away from the sun, away from the earth. It's opposite the direction of the sun. So that's where Webb telescope will be placed. It will keep it super cool because it's so much further out, and it can stay stable there. It will rotate with, it will be in line with the earth, and as the earth revolves, it will revolve with the earth, but it will always stay at the same direction, so that its sunshade is always facing the earth and the sun and the moon. So the sunshade will always protect the telescope and the instruments. Okay, so this is in L2 position. But the challenge is it's going to be very far away, so the rocket is going to have to place it in that position. And unlike Hubble, there can be no mission that services this telescope in case something is wrong. Okay, so that's the L2. It's 1.5 million kilometers away from Earth, whereas Hubble was just 570 kilometers. So you can see the two. That's going to be a big challenge. So the instruments are nearly all infrared. So there's mid-infrared and near-infrared. So already Arjun sir has told you what we can see in near-infrared and mid-infrared. So another last special innovation I'll tell you about is one of these instruments called the NIR spec has micro shutters. You know how your camera has shutters? This has, 100 shutters that operate at the same time. So basically, they can orient themselves separately. Some can open, some can close. So you can get multiple objects at the same time, and you can get 100 spectra at the same time. So you can basically, you're processing a lot more data at the same time and getting a lot more information or images from the objects that you're observing. Okay, so yeah, that's a lot of challenges that have led to innovations. So let's take a final look at the parts of JWST. It has a primary mirror with 18 hexagonal segments. It has a secondary mirror, which reflects light gathered from the primary mirror into the instruments. Okay, the science instruments, they're all protected. That's a very important part of JWST. It houses all the science instruments. There's a 5-layer sun shield. There's also a solar power array. And again, because of the L2 position, it's always going to face the right direction. Okay, so yeah, that spacecraft bus contains the control and the communication subsystems. So finally, how will JWST work? I'll show you a short video. It's got a different kind of telescope system. This is the primary mirror, and the secondary mirror, you can see it goes, and then it's a little bit off focus. So that helps astigmatism, which means it helps focus it better and not create color corrections. Okay. So now I've said this is the biggest telescope ever going. It's got a folding mirror and a folding sunshade for this kind of launch, and it's going to go to L2, which is much, much further away. So for this, you need a special rocket called the Ariane 5 rocket for launching. So JWST launch is coming up soon. It was scheduled for 22nd of this month, and now it's due to some more technical errors, it's scheduled for 24th, and it might shift a little bit more, but that's why we wanted to inform you all about JWST, because it's going to be the big telescope, the next generation space telescope, as it's called, and it will be the biggest telescope of the next decade. So we will all witness its launch soon. So I'll just end with a short video of what happens next. Okay, once it launches, what happens after that? Okay, so it's going to take 6 months for reaching its L2 position, for unfurling its mirror and sunscreen and everything else, and for testing. So only after 6 months will scientists be able to see real data. So this is a very exciting video which shows you how everything is slowly unfurling once it reaches space. So, the mirror is all folded up. The sun shield is all folded up. Remember, the sun shield is 5 layers. So all the layers have to make its way down. Okay. So that's the mirror. On both sides, there are 3 mirrors that are folded up into that drop leaf kind of fold. So this is all like origami. It's all going to be unfolded itself. So yeah, you can see how everything is unfolding and slowly opening up. Let's see when the mirror opens up. This is the sunscreen now. Okay, and like I said, it's going to take 6 months, and JWST is already ready to start on its science. There are many proposals given by scientists. Okay, so that's the secondary mirror unfolding. Those are the primary mirror sections unfolding. And JWST has come up with innovations that that nobody has ever come up with before. So it's a marvel of engineering, as well as the objectives it's going to try to achieve. Okay, so with that, thank you. And I hope you all enjoyed the, learning about JWST, which is going to be our premier telescope for the next decade. Arjun, should we take some questions?
So much for the talk, and thank you so much for telling us so much about the JWST. So yeah, so I can see that students were having a lot of questions. So I hope all of you really enjoyed learning about the JWST, and now you guys are also excited about the JWST launch, because let me tell you, the respect and the kind of the scientific discoveries that Hubble made will dwarf in comparison to what JWST will be able to give us once it is concluded. So that is the impact of JWST is going to be, right? So let's hope that it gets deployed in its orbit perfectly without any any kind of anomaly or any kind of damage to any of the instruments that we have prepared. Because here is the thing, like Mila ma'am said, this JWST will be very far away from Earth. It will be at a distance of 1.5 million kilometers, which is actually around 5 times as far as the moon, right? So when we launched the Hubble, you guys must be aware that when we launched the Hubble, there was some problem with its mirror. But at that time, because it was in the lower Earth orbit, very close to Earth, so we were able to send astronauts who actually went in there and were able to rectify that and be able to repair that, right? And there were many other repair missions of Hubble which subsequently went. But this is something which won't be possible with the JWST because it will be very far away. So we have to ensure that every single thing which is there in the JWST is working properly, because the thing is that it has been in works for the last 17 years now. Sorry, 15 years now. It started in the year 1996, right? So you just imagine, like, okay, around 25 years, sorry, not 15, around 25 years, right? That's how much time we have taken to develop this, a 7 billion giant telescope, which we are going to send into space. And if anything is to happen to them, so it will be a disaster, right? So yeah, so that is the reason that everybody is very nervously waiting for it to get launched and launched properly. So with the students, I am seeing that many of you are having questions. I was answering your questions in the chat also, but if you have
so we'll just take a couple of questions, and
yes, and we will be taking a couple of questions. So one question I was going to take, yeah, ma'am.
So one of them asked, are we looking back in time, or how are we seeing the most distant objects? So those two are related. see the oldest objects have moved the furthest out, so they're still going to be sending signals, and it's going to take a long time for us to reach us, but it's going to reach us now. But they generated those signals 13.5 billion years ago. So time and distance is correlated, and we are going to look at those objects.
Yeah. So to answering further on this question, basically what happens is the light year, if you know, it is the distance traveled by light in 1 year. So the more light year you travel, the more distance you are taking for the light to come. So if you're looking at 5 billion light years away, we are actually looking 5 billion years back in time. So this is the reason that if the JWST is expected to look 13 billion light years away, so it means it will be looking around 13 billion years ago. And that is the time when the Big Bang happened. And there's the reason that we are saying that if we are able to look the light of that far distance, we may be able to see what happened at the beginning of the universe, right? So this is it. Let me take a few more questions. One question is saying, sir, for how much time this JWST be expected to stay in to give us the data? So basically, this mission or this telescope is originally planned to work for 10 years, but even Hubble was planned for 10 years, and it has been giving us data for the 30 years now, right? So let's hope for the best. Let's see, but it will be giving us the data for at least 10 years. All right. The next question I am going to take is this. How to make sure that it will not destroy the atmosphere? No, Amrita, it like every other rocket, like any other rocket, but does not destroy the atmosphere. Even it is not going to destroy the atmosphere. It is going to basically pierce through the atmosphere like all the other rockets, right? Can you tell why sun shield? All right. So Pradeep have a very interesting question. He says that, sir, can you tell why the sun shield is pink? So,
and I think a few people asked that question. So let me answer that.
Actually,
so it's an interesting question, because yes, some people have asked, why is it not silver or white? Because that would reflect more. But it's made of a special material, and it is that special material called Captain, which is a lightweight material that, in addition to an aluminum coating, that based on that is what the sun-facing side looks pink. So that is the answer to it.
Yeah. Thank you so much, ma'am, for the answer. So, okay, students, so we are going to take 2-3 more questions. So please ask your question. The next question I'm going to take is, if the mirror get damaged and we can't repair it, then the mission fails, right? Unfortunately, yes. That is the worst nightmare that the scientists of ISRO and every astronomer is having nowadays, that what if it does not go perfect into the space? And that is, let's see if we can avoid that.
That's why it has gone through a lot of testing. Yes. So you have to be confident in that.
Actually, students, first the JWST, when it was being designed, in which year it was first designed to get launched? In the year 2014. Now it is 2021, that to December 2021. So why do you think why so much delay? Because we are being extra cautious. We are making sure everything is going through multiple testing, multiple strain resistance and tests, depending on what kind of adversities it may be facing that far out in space. And we are very cautious about it. And let's see if the scientists have done a wonderful job in that. Yeah. How many light years will the JWST travel? So JWST, one student asked that, sir, how many light years will JWST travel? So JWST won't be traveling light years. It will be traveling 1.5 million kilometers, right? That is like 1/100th the distance between Earth and Sun. Light years itself is around 9.5 trillion kilometers. That is like too big, right? So which is, it will be looking back billions of light years, but it is not traveling that much distance. Yeah. All right. So Shrishti has an interesting question, sir. Why do ISRO does not have any space telescope? Shrishti, yes. Basically, in that regard, ISRO is a bit behind NASA, and
no, we do have AstroSat that has contributed.
Yes, basically we also have a space telescope of our own, but not of this caliber, because the objectives of ISRO has been different till this time. But with the advancement that we have been making, the structure of ISRO and all, you can expect us to do more such kind of scientific discovery and scientific missions in future in the next 10 to 20 years. Just hope for the best. Yeah. So here, All right. So ISRO,
Yeah, I think we should
JWST,
close
not
up probably.
at the current moment. All right. So students, so this is all about the JWST. Again, I would like to reiterate to all of you, students, please, if you have not done your onboarding till now, please do it at the earliest. If you are facing any problem with the onboarding, please write to us at hello@nationalastronomy.org. That is the mail, right? Just type whatever query you have in the mail and we will make sure that it gets resolved. All right. So don't delay it now because the dates to the exams are very close. I hope you guys are reading your material. I hope you guys have gone through the entire material of for your grades. And let's see. Yeah. How does infrared light go back in time? So, okay. So Sumita is asking. So basically, infrared light itself does not travel back in time. What happens now? Light being even after being the fastest traveling entity in the entire universe, it also is limited, right? It also has a limited speed. That limited speed though is 3 lakh kilometer per second, that fast, but still limited, right? So it means that in 1 second it can only travel 3 lakh kilometers. If you want to travel 150 million kilometers, but that is the distance between Earth and Sun, the light takes 8 minutes 20 seconds, which you all must have learned in your school. But just imagine if the distances in the space are in billions and trillions of kilometers. The light itself takes years to travel that distance. So if the object which we are trying to see is, let's say, around what we say, is at a distance where from the light itself is taking billions of years to come or 13 billion years to come, that light would have originated when the universe was first formed. And that's what we are trying to see here. What the infrared is going to do is it is going to only help us to see those light. Why? Because these infrared, it can actually move through the clouds and all the basically all the small would be gaseous or any other hindrances that might be experiencing in the universe. It may be able to penetrate that, right? And that's the reason that we are trying to look at in the infrared. Yeah. So Khadej is saying the last date of onboarding. So Khadej, the last date of onboarding is 25th. All right, 25th of December. Please ensure you do it before then. Yeah. All right.
And some kids still asked about the exam dates. So where would they find it?
So, all right. So the exam dates are on our NEC website. So basically, I think that we have already told you about it. So let me just show you. All right. Let me just
just show them the website.
Let me just share my screen and show it to you. See, if you go to our website, now this is the website, nationalastronomy.org, right? So just go to this website, www.nationalastronomy.org. Yeah, this is the NEC website. You all must be knowing this. Right over here on the top only it is written NEC Olympiad dates. You can always go here and check your NEC Olympiad dates. And not only that, students, in this, basically, if you explore this website, everything is listed for you. That is the what will be the pattern of the exam, what will be the duration of the exam, what will be the marking scheme of the exam. Everything is mentioned on the website. So please go through this website properly, right? And then you will be able to figure all of them yourself. Yeah. So, okay. So this was all, students, from my end. So with this, I would like to tell you, like, we are coming back on Monday. Yeah. So so we are going to have another very interesting session on observational astronomy. Let's see if you guys enjoy that. So see you on Monday, everyone. Till then, have a great time. Yeah. And bye-bye. Yes, you can leave now.